We now know a lot about entanglement theory. We know how to detect entanglement. It's about the time we talk about how to use entanglement. So what is it good for? And this is usually under the umbrella term of quantum communication. Or entanglement-assisted quantum communication. Now, if we want to talk about quantum communication, we should first talk about classical communication. Because in principle, the idea is that quantum protocols will improve the classical protocols, but for this we first of all need to know what the classical protocols are. So, how does classical communication work? How does it work when you're sending gifts to your friends?
Are you asking about encryption or just...
No, it's just like the bare bones idea.
Send a bunch of ones and zeros?
Exactly. So the first step is to decompose the message into bits. So, for example, we take the message hi and we map it to 0, 1, 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1. Something like this if you use something like ASCII, or you can use Morse code or stuff like that. Do you actually still know what a Morse code is? Okay, good. The second step is to transmit the bits. The bits, and we go from sender to receiver. This is rather obvious, it's just how we call those two people. And the third step is to convert back to text. So this is extremely intuitive. And now here's an idea. Here are two letters, H and I, encoded in ASCII, and these are, or should be, 8 bits for one letter. So if I want to send you a word with two letters, I have to send you 16 bits, or at least, disregarding handshakes and encryption and all of that. But the idea, or the question that one should now ask is that, can we send more information with qubits? Okay, so if I would be sending qubits instead of bits, can I, instead of sending 8 bits, send, for example, 7 qubits or 6 qubits? Or I can even say, like, can I do this in 7.2 qubits, which just means that asymptotically this is the number of qubits that you have to do, because you can always merge stuff, you know, and things like that. And so what do you think the answer is?
The answer is no.
Why?
Because Professor Hammerer said so.
Yesterday?
Yes.
Okay. Did you do this yesterday?
No, we will do this next week.
Oh, wow. So you can either pretend to be very smart next week or kind of bored. So, no. And the idea is that, and the question is that it is not possible to communicate n classical bits by transmitting less than n qubits. So is it clear that if I can do it with n bits, I can do it with n qubits? Yes, because instead of doing this, I'll just encode this as a computational basis 0. So I just say, now I send this state, now I send this state, now I send this state, and so on. And you can always measure in the same basis and get the bit back, okay? So if I can do it with bits, I can do it with qubits. And the answer is that, well, and that's the best we can do. Sorry. And this is implication and a very abridged and simplified version of Holevos theorem. So I hope that next week you'll actually prove the whole Holevos theorem. But now we want to go to a different idea. Well, okay, just sending qubits doesn't really help, but what if we would have some entanglement and send some qubits? Would that work better? Did you do that? You did that yesterday? Now this looks a little bit strange, but actually before organizing this course, I actually roughly asked Professor Hammerer where he wants to go, and that's why I picked quantum non-locality, because he said he wants to go towards metrology, so that we should somehow diverge. So I was not expecting this much of an overlap. And I even asked you last week whether you did this. So, new idea. Entanglement-assisted communication. So now I would start explaining superdense coding. Should I explain this or should I skip this? Okay. What?
I don't mind hearing it twice. I don't know if everybody is in that course.
Okay, so who wants to hear this again?
I want to hear this first time.
Okay, then it's fair enough to actually go through this. So the idea here is called superdense coding. And this is a protocol to communicate two classical bits using one Bell state, so this one. So we need 1 times this one, and 1 times transmit a qubit. Let us go back to communicating a single bit. If I want to communicate a single bit, what Alice can do is that if the bit she wants to communicate is 0, she prepares the state 0 and sends it to Bob, and then Bob measures in this projective measurement, or this POVM. And if the bit is 1, Alice transmits 1, and Bob has to measure in the same basis because he does not know what the value of B is, so his action cannot depend on B. And what we get is that probability of Bob obtaining outcome A is given as the trace of the state Alice prepares, which depends on B, and the projector AA here, right? Where now this A is either 0 or 1. Is this formula clear? So this row B is either the 0 or the 1 state. Bob measures in this basis. This is the probability of Bob observing the outcome A, depending on the state B. Now plugging this in, we get trace BB A. So what I said is that here is that if the bit is 0, Alice prepares 0, which is just a projector like this, but now we should replace this B with 0. If B is 1, she prepares 1, which as a density matrix is again a projector, but you would replace B by 1. And what you get here is delta AB. So, which means that the measurement outcome of Bob is going to be exactly equal to the bit transmitted by Alice. And the main idea here is that these two states that Alice is preparing are perfectly distinguishable. If you give me one of them, I can perfectly tell you which one you gave me. Because I can just do this measurement and obtain the value exactly. Now, the idea of superdense coding is essentially the same, but we are going to have 4 perfectly distinguishable quantum states. And quantum states that are perfectly distinguishable in a simple case form an orthonormal basis, right? These two vectors are perfectly distinguishable because they form an orthonormal basis, which means that this is a measurement that we can apply and we can redo the calculation and arrive here, okay? But if I would have, for example, a 4-dimensional Hilbert space of 2 qubits, and I would give you an orthonormal basis, I would have 4 states, and these 4 states are perfectly distinguishable because I can measure in the corresponding basis and get exactly back the value. This is the whole idea. Are there any questions about this? Very good. So, what we will use is the Bell basis. And here we'll have our favorite Bell state. We'll then have the state which is almost the same but with minus. We'll have the state which is with plus, but now it's not 0, 0, but 0, 1. And we'll have the state psi minus, which is the same as above, but with minus now. And now we can check that this is a basis, because if I do inner product of the first one with the second one, I get +1, -1, so that gives me 0. And if I do inner product of this one with any of the other ones, then it never contains 0, 0, or 1, 1, so I'll get 0. And you can do all of the other inner products and to find out that this is in fact a basis. Moreover, I will now introduce some unitaries, and this is going to be the sigma z. It's the sigma x and the sigma z, which are the Pauli matrices, and they're unitaries. So these are unitary matrices. Moreover, they have real components, which means that phi x star is equal phi x transpose, and phi z star is equal phi z transpose. And whenever you don't remember how the Pauli unitaries look for Wikipedia and try to be consistent with Wikipedia. Which is not only good because other people can find out what you did, but then 5 years down the line, you're going to be the other people trying to find out what you did 5 years ago. And if you're consistent with Wikipedia, it's going to make your own life easier. And these are such that if we apply z to 0, we get 0. If we apply z to 1, we get -1. If we apply x to 0, we get 1. And if we apply x to 1, we get 0. So we call this a phase flip and a bit flip. No. Here's the neat thing, or the thing that all of this is built on, is that this state is essentially the same as this state, but we flipped the sign from plus to minus if there was 1. But this is what sigma z does, it flips the sign if there's 1. So you can check that this can be written as sigma z times identity on Bob acting on phi plus AB. So if Alice applies sigma z, she goes from this, she transforms the global state by doing local operation from this one to this one. What happens here is that we flipped the first 0 to 1 and the second 1 to 0. So already looks like this one. Again, explicitly verify this. And the last one, I'm going to look into my notes now because I don't want to get this wrong. So we first apply sigma x to go from phi plus to psi plus. We are here, and now we apply the sigma z to flip this one sign. And if you do it the other way around, you would flip the other sign. Or in other words, here one has to actually make sure that you write these unitaries down in the correct order. They don't commute. Very well. With this, we can now describe the protocol. So at the beginning, we have that Alice and Bob share the bell state, this one, and Alice wants to communicate 2 bits. Communicate 2 bits. This means that Alice has 2 bits that Bob does not know what they are. If Bob would already know what these 2 bits are, they don't have to communicate the 2 bits. But the point is that Alice knows what these 2 bits are, Bob does not. And we go like this. Alice applies local unitary. Based on message. To her half of the bell state. Again, this is important. She cannot apply global unitaries. She cannot access the part of this state that is held by Bob. She can only apply unitaries or transformations of this form because she cannot access Bob's system. Right? So if the message is 0, 0, the unitary that Alice applies is identity. If the message is 0, 1, the unitary that Alice applies is sigma x. So here we map phi plus to phi plus by doing nothing. Here we map phi plus to, if we look it up there, to psi plus. If it's 1, 0, the unitary that Alice applies is going to be sigma z. So we map this one to the one with the minus. And if it's both, then Alice applies and mapping the bell state to the psi minus state. Then again, Alice is touching only her half of the system always, so because that's all she can do, but she changes the global state to one of these 4. And the second step is that Alice sends her part of the state row AB that they share, so row B is one of these 4, to Bob. This is again important because if Alice would not send her part of the state to Bob, Bob can only apply local transformations and local measurements. If Alice sends her part to Bob, Bob can measure the whole quantum state because suddenly he will have both of the qubits in his lab. And the first step is that Bob measures in bell basis. Since those 4 states form an orthonormal basis, if Bob measures in a bell basis, he will know exactly which of these 4 states he has in his lab. So he will know exactly which of these 4 states he used to share with Alice. So he will know exactly which of these 4 unitaries Alice applied to her half of the state. So he will know exactly which of these 4 2-bit strings what Alice wanted to communicate. And that's all of superdense coding. It's just this kind of trick of, well, if we have entangled state, I can send you my half of it, but do something to it before and basically map it somewhere in the bell basis. Are there any questions about this? Is this more clear or less clear than yesterday? So now we're going to do something else. Here we asked about transmitting doing classical communication and transmitting classical information. Now the question is, can we transmit quantum information? Which means, can we transmit an unknown quantum state? So if you know what state you have, so you have for example, which one of these 4 I have, I don't have to transmit quantum information. I can just tell to Bob, I have one of these 4 states. But if I have, in principle, unknown state, because I was somehow processing it or I got it from somebody else, I cannot just measure it and tell Bob the outcome of the measurement, because there is no measurement that would exactly, in a single shot, tell you which quantum state you have. So the question is, can Alice actually send a qubit to Bob, or transmit the state of a qubit to Bob? Now, of course, it's rather intuitive that if Alice can transmit one qubit to Bob, then she can actually transmit the qubit to Bob, and Bob will receive the quantum state she wants him to have. And there's also another idea, is that if Alice can transmit one qubit to Bob, then they can create the Bell state between them. Because Alice can prepare this Bell state in her lab locally, and she transmits 1/2 of it to Bob, and then they'll start sharing this Bell state. So now the idea of the following is, can we do this in reverse? Can we, by sharing a Bell state and using some classical communication, transmit a quantum state from Alice to Bob? And so the idea is that we are going to use entanglement in the form of phi plus classical communication to send a state of an unknown qubit to Bob, and this is called the quantum teleportation. This thing. And quantum teleportation is actually, I would say, somewhat important protocol, not because, for two reasons. First of all, because it's used in quantum networks to create entanglement between remote parties, which I'll then discuss after I explain the protocol, but also because quantum teleportation appears as a subroutine in other things that we might do. So sometimes what we can do is that we can use teleportation to somehow store some quantum information or store some quantum channel and apply things retroactively and things like this, if it will work out. So it's good to know this because it pops up in papers. It's a well-known trick that people often use. Okay. So what are the Hilberts? So rho I will be the input state. And the important thing is that this is unknown. We don't know what it is, and we cannot measure it, because if we would measure it, we would destroy it. So we have to send it to Bob without destroying it and without actually sending it. And so what are the Hilbert spaces in this, or what's the Hilbert space in this protocol, is that we have the Hilbert space on which this state lives. All of them will be qubits, but this will live on the HI. And then we have the phi shared between Alice and Bob, phi AB. So there's going to be Hilbert space A and Hilbert space B. The rho I lives here, and the phi AB lives here. But Alice has access to this, and Bob has access to this. So there's somewhat a misalignment between this tensor product and what Alice and Bob have access to. And this is somehow good to sit for a while and ponder about this, because this is like a easy source of mistakes and misunderstandings. But when you think about it, it's still the same thing, that Alice and Bob share the Bell state, and each of them have 1/2 of it, but now Alice also has another quantum state. So how does the protocol work? The first thing is that Alice measures on the Hilbert spaces HI tensor HA in Bell basis. The Bell basis, this one, lives on 2 Hilbert spaces, so Alice must measure both of her Hilbert spaces. Okay, so now we are going to have this state, but we are going to apply the measurement to this and 1/2 of that. We'll see that explicitly in the calculation. Then Alice communicates measurement outcome. So there's 4 elements in the Bell basis. So how many outcomes do we have? Yeah, exactly. And how many bits is that? Yeah. It's essentially these 4 possibilities again. And the 3 is that Bob applies local correction. Based on the measurement outcome. And this is important. If you don't base the local correction on the measurement outcome, you're not going to get what you want. It has to be based on the measurement outcome. So Bob has to know what measurement outcome Alice got. Did you also do the explicit calculation? What are the key steps or key tricks? Or did you just write down the whole protocol and just went brute force into it?
We express like 0, 0 states in terms of the Bell basis and on the other tensor product.
Okay. So now at least this might be new to you, because this calculation I usually do is based on like manipulating partial traces and all of these things. And tricks involving the Bell state. And I'm missing pluses here, right? But for that we'll need some preliminaries. The first one is that if you have a Bell state and you do a partial trace over A, what do you get?
1? No, wait.
It has to be operator.
Yes.
So these are now products of operators, right? You have to remember that whenever I write something like ij kl, this is equal to ik tensor jl. So how do we do partial trace of this one? You just do partial trace of these two things, or this projector, and you realize it's equal to 1. The same thing happens here. You just partial trace those once and it's equal to 1 again. A different thing happens in the other two cases, because you're doing the trace of it is not a projector, it is like an off-diagonal element 1, 0, and the trace of that is 0. And the same thing happens here. Which means the yellow cases heroically die in the partial trace, the blue cases survive, and we get 1/2. And here's going to be the 0, 0 plus 1, 1, which is complete mixture. Okay. We'll also need some tricks with the transposes. And so another thing that we will need is that if I have transpose of A and B, this is B transposed, A transposed. Do you know this from linear algebra? What's this then?
You cyclically print.
So if you know this, you can get this by somehow bracketing it like this and treating this as one operator and undoing the brackets in 2 steps, and you'll get here. And if you want to prove this, you can just do it in coordinates and just write down this, what's the ijth element of this, and you will see it's that. And the last trick that we will need to know is that if x is an arbitrary operator on Alice, so x can be written as sum over ij, xij, ij, then we will prove that x times identity on B when acting on phi plus on AB is going to be the same as identity on A times x transposed acting on the same state. So then this is going to be actually the contribution of the first half of the lecture for those of you that are bored so far, because this is a trick that again appears quite a lot because this state appears a lot and there's usually operators around, so this is trick that we have often enough. So we are going to start here, we're going to somehow do some modifications and we're going to show that it's equal to the same as this thing. And we do the calculation by expressing everything in coordinates. And here we are going to get, or rather, I'd write this thing that we have here as sum over I. Now, this is a tensor product of operators acting on a tensor product of vectors, so we are just going to get this sum over I, and here we are going to have x acting on I, tensor I. So I just split this tensor product into the explicit notation and then just acted with the first operator on the first element and the second operator on the second element. Got this. Now, into this, I can plug in that I can express the operator using this xij, using its matrix. So I'll have here now j and k because I already used I, so I have to use j and k here. And I'll get x, j, k, and here I get j, k, I times I. Now, of course, this is nothing else than delta ki, because it's an inner product of an orthonormal basis. So xji j times I. What's this? Vector operator. This is just a number. So I can move the number here in the product because it's just a number. No, this one's j, this one's j, this one's I, and this one's I. Here.
Somehow insert an identity.
Yeah, could be probably done also in that way. But the trick here is that if life would be so easy that we would have ij here, what would happen is that would essentially look like the formula that we had when going from here to here, right? Because here we have x when acting on I gives you sum over j, j, I, j. So if we would have I, j, I and summing over I, this would be nothing else than x acting on j. So doing the trick this way is a little bit, you have to like pack stuff back. If you would write this thing and just undo it in that way, you would arrive exactly here if the coefficients would be I and j. Well, but life is hard and the coefficients are not I and j, they are j and I. And we cannot just switch coefficients willy-nilly. Well, we can, but we have to pay the price for that. And the price that we pay is that this becomes a transpose. Right? Because xji is nothing else than the ij element of x transposed. This is what the transpose does, it switches it to indices. But now the coefficients are I and j, and I here summed over I, so it's the same as here, except for they are renamed in the other way, we can pack it back up there. And now we just need to pull the X transpose out of the bracket. And we get identity acting on A, because, well, there's an identity here always. X transposed here, and phi plus here. Which is exactly what we wanted up there. I'm going to leave this half of the board like this, so you can always refer to it. I'm going to erase this, and I'm going to do the calculation here using those 3 tricks. And now, depending on your preferences, the next calculation is either going to be really annoying or quite fun. I'm in the quite fun camp, but I mean, if you find it really annoying, I don't blame you. So I'm going to do a little bit of notation. I'm going to denote the bell projectors like this. P2 is going to be phi minus, P3 is going to be the psi plus, and P4 is going to be the psi minus, and in general we have that Pi is equal to Ui times identity acting on P1, which is just the phi plus projector. And this Ui can be either identity or sigma z or sigma x or both of them. So what we now want to do is that we want to get the state of Bob after Alice measures. Since Alice measures the H and I Hilbert spaces, this one and this one, we're going to have partial trace over those two. Because we want to compute the post-measurement state. Here we have the input state, or the initial state of the protocol. And here we are going to have the measurement operator. So what's going on here is that this is the state we have at the beginning of the protocol. It's this one. Here we have the measurement that Alice is applying times identity on Bob. And we want to know what will the Bob's state be after Alice observes outcome I, which means we have to trace over those two systems, to trace them away to see what we get. Now, if you would assume that this Pi is a projector as it is, you can imagine that it's going to sandwich just the part of the system that lives on I and A, okay? If there would be no B, it would be rather obvious that this is how we compute probability. That's the Born's rule, or, you know. Now, since we have a B, but we are not measuring B, we are just measuring these two systems, we have to perform a partial trace because we are actually going to have some kind of post-measurement state on Bob. And this is how we obtain it. This is how we get it. Okay? In a simple case, if I would have just Alice and Bob, so this is like an example, and they would share something like rho A tensor sigma B, and Alice would measure some kind of P of M MA, and Bob would not do anything. And I would want to, in the same way, compute the post-measurement state on Bob. I would just get this trace rho A MA sigma B. Okay, so this is what you would get for product states. And this is rather easy to check because Alice and Bob share two completely uncorrelated, unconnected quantum states. Alice measures, and this is the probability of her observing the outcome A, and Bob still has his state because we never touched it. This is the same thing, except for this state is entangled. But since entangled states belong into the linear span of product states, the same form, well, this part of the formula extends, you know? Except for we are now replacing this by some kind of more complicated state here. And we also have this additional system here. But you can also in your mind merge I and A systems and see this as some kind of A prime, say. Are there any questions about this? Then again, if you somehow, in the unlikely case, you revisit your notes and this is not clear, please come and ask me. these things are also usually not too much explained when you're reading scientific literature beyond textbooks, because somehow everybody knows this is how we do it. Okay, so now what I just want to do is that I want to express this projector using that form. No. It's now important to keep track of what lives where. Is this thing correct? So what I did is, actually, is this thing correct? No, because the unitary would just transform the first, this first vector here, but not the second one. So we also have to have the unitary from the other side. But since now this is not the ket, but the bra, there has to be a star here. It has to be the adjoint one. Because if you're acting to the left, to this one, you have to go with the adjoint, because then it unadjoins itself when it comes inside. So we also have to have the adjoint here. And now we can even make this bracket more explicit like that. There should be one big bracket around. All right. Now the trick is to realize that this acts on I, so I can, instead of writing it like this, I can write these two operators as identity times this acting on AB, and this acting on I times identity on AB, and push it that way. So what I can do is that effectively I can push this row here. So I get here trace IA, identity on I times phi plus on AB. And here I get rho I times UI. Here's the phi plus on IA. Another identity times UI star times identity on B, that bracket, that bracket. Now I'm going to use for the first time this trick, but here's an important thing which can make your calculations completely wrong. I want to use it on this rho I because I want to clear everything out outside of the rho I system. So I'm going to put it here, but then it will end up before the unitary, okay? Because you have to pull away the unitary, apply that trick, and then put it back. Clear, or should I write it? So the thing is that if I would have x times y on phi plus, I would write this as identity times y, x times identity on phi plus, and using that trick, I would get identity times y x transposed on phi plus. So you have to put this one before. Now here's the problem. I denoted this row I as an input state row living on Hilbert space I, but since I now moved it around, it's not living on the Hilbert space I anymore. Nevertheless, for consistency, I should still denote it with I. But please bear in mind that now it actually lives in Hilbert space A.
On the row I?
Oh yeah. row I living on A. What can we do now? Now we start tracing because we realize that here's an identity on I, this is a Bell state, and here's an identity on I, this lives on B. So this partial trace will just come here, because it's the only operator in the product that's not identity on the Hilbert space I. So the partial trace will act only on this state. This is just a very iterated way how we define the partial trace, which was that if you have identity and operator, then you can, in the trace, then you can pull the partial trace inside. So if you look at the definition of the partial trace, it was essentially this, except for now we have many of these identities here, not just one, but I could of course reorder the product in such a way that it would be just one identity and then this operator. So since the partial trace over I acts on this one, and it's just the partial trace over I, not over A, we use, where was that thing? This one. And we get 1/2 identity. That's how this half comes in. We are still left with partial trace over A. And now all of these identities disappear. And here we are left with just this phi plus, living on A and B. And here inside this square bracket, we are left with ui row I transposed, still living on A, and ui star, then their identity on B. Now the trick is to either use that trick, but to use it in reverse when going this way, or what you can use is that trace has this cyclic property that you can always bring stuff from one side of the trace to the other, except for this is not a trace, this is a partial trace, but this is an identity, so it still works. And you can always check for product operators, see that it works for product operators, and if it works for product operators, then it works for everything by the linear argument. So we are now bringing this thing here just by linearity of the trace. Now, if we would be tracing over B, we would be almost done because the partial trace would act only on this operator by the nature of the same trick, but now way simpler. But that's not the case, because we're partial tracing over A. But this is the Bell state, so we can again use that trick. And where does the row I now live? So in the beginning I say it lives on the Hilbert space I, that's why I denoted the row I. Then I started explaining here that, well, we use this Bell state trick, so now it lives on A. So where does it live now?
B.
Yes. And now we can do what we wanted to do all along, which is to say, well, according to our definition of partial trace, it will just act over here. There's 1/2 missing over here. And we'll get again from this partial trace acting on the Bell state, 1/2 identity. So we get 1/4 ui row I, but now living on B, transposed ui star. And that's all transposed. Now just the last thing is to undo the transpose. And we get ui row I, but now living on B, ui transposed. So after Alice does all of that, this is what Bob gets. Now, the only thing that Bob needs to do is to get rid of this unitary in order to obtain the input state rho I now living on B. But I mean, if Alice tells to Bob what was the outcome of her measurement, she's essentially telling him the I, and Bob can just apply the inverse of the unitary and get rid of this. Also, in like with probability 25%, this will be identity and it will just work out of the box. Yeah, so this is teleportation. I hope the calculation was at least sufficiently different to be interesting. Which one did you find easier to follow?
The other one.
I think the other one, but this is a good exercise for the techniques of partial trace and that trick to show as well.
Good. So an interesting application of this is called entanglement swapping. And this is somehow related to the, am I again repeat? This is related to the problems of noise in quantum networks. Because Alice does not have to teleport a state, she can teleport 1/2 of entangled state. So what can happen is that we can have Charlie here, so we can have Charlie, Alice, and Bob. And we can have here source of Bell states between Alice and Bob and Alice and Charlie. So this is the phi plus, and this is the phi plus. And now Alice has to have two systems. So what can Alice now do is that she can apply the teleportation protocol with Bob. So Alice measures here in the Bell basis, tells the outcome of the measurement to Bob. Bob applies the local unitary correction on his side. And what happens is that Alice will be left with nothing, but Charlie will share entangled state with Bob. Because essentially Alice is going to teleport this connection here to this connection between Bob and Charlie. This is called entanglement swapping. So for quantum teleportation, we need entanglement and we need classical communication. The entanglement part is hard to do experimentally because you have to share entanglement between parties. And then you have to measure it, and then you have to transmit the classical communication. So somehow the entanglement, you can assume that you have it at the start of the protocol because you can start the protocol whenever you get the entanglement. But then the classical communication can be seen as a little bit of a bottleneck because you have to send the message and Bob has to actually do something based on the message. So the question would be, can we do something like teleportation but without the communication? Then it would happen almost instantaneously because Alice would just measure and that would be the end of it. And yeah, can we do something like that? So, does anybody have any physical intuition about this? Is it like you don't want to answer or you think no?
I mean, I have no intuition about it.
So what we did in teleportation is that we took an unknown quantum state and transmitted it to Bob by using entanglement and classical communication. My question is, can we drop the classical communication part?
No, kind of violates the principle of nothing being faster than light.
Yes, that would violate the principle of no faster than light communication. It's actually, things can be faster than light. Like for example, if you take a laser pointer and point to one side of the moon, and you flick your wrist to point to the other side of the moon, the dot will probably go faster than the speed of light, but it's okay because it's not really transmitting information. Yeah, so we will now want to show that this is actually the case and nothing is transmitted faster than the speed of light. So quantum theory does not violate special relativity. To a small extent, this is a little bit non-trivial because those are two completely different theories and there is no obvious reason why one should not violate the other except for it would kind of make sense in the big picture. Well, I mean, no, really. At the beginning, when you take non-relativistic quantum theory and special relativity, they just work in different regimes. So one could have potentially violated the other. So what we do here is that Alice and Bob share some state rho AB, and Alice measures measures whatever P of EM MA. What is going to be the post-measurement state of Bob and with what probability? So let's start with the easy one. The probability of Alice observing outcome A is?
Trace MA row A.
Yes. But here has to be also identity on Bob. Because Alice measures this, which means that globally they measure this. And now the post-measurement state on Bob is going to be something like sigma A, which is going to be, well, 1 over PA, because otherwise it would contain the probability. And here's going to be the trace of A, row A, B, MA times identity B. So why I put this here is just to normalize the trace, because otherwise the trace of this would be exactly that, so we have to divide by that. But if we assume that Bob would somehow know this outcome, this is exactly the state that he would get. But now the question is that the thing is that Bob does not know what the outcome is. So he does not know that he has this state. He can only say that on what is the average state I have, or with what probability do I get what. So on average, Bob will have, with probability PA, the state sigma A. Now here we get the two probabilities. This obviously cancels. And we get trace over A of row A, B, MA times identity B. And the trick is now to take this trace and sum over the P of EM. What is this equal to? Yes, this is just identity on A. So it's identity times identity, which is identity. And in the end, we get trace over A, row AB. And this is usually referred to as no communication theorem or no signaling principle, because on average, Bob only will see this state in his lab. So not only that Bob does not know what outcome A Alice observed, he does not even know what P of EM she measured. You know, because maybe if he would at least be able to know what P of EM she measured, they would then be able to send some information by measuring different P of EMs. You know, like 0 is this P of EM, 1 is this P of EM, just measure and send a message. But no, the average post-measurement state on Bob does not depend on any of those things. Hence, Bob has no way of finding out what was measured and what outcome was obtained. So, no violations of special relativity. Now, in the end, I wanted to do something that you usually don't find in most lectures or most courses. I wanted to do a protocol that's, you know, not the ones that you read about in every paper. So now I'm pretty certain that you haven't done this in a previous lecture. And this is going to be the protocol for quantum anonymous transfer. So we can imagine the following scenario, or one of these two scenarios. The first one is that we would want to hide a whistleblower, which means that we want to have one of us send the message to everyone, but we want to ideally hide who that person is. And we even want to hide who that person is, even if n-2 of us would somehow try to collaborate, you know? Because if n-1 of us collaborates, then we know that it was not me, it was not you, it was not you, so it must have been him or her. But if n-2 of us collaborate, we still don't know which one of the remaining two it is. So we want to hide a whistleblower that's going to broadcast the message to all of us. Another thing where this could be applied would be, for example, if we would want to gather some statistics, but people don't want to reveal that their answers. So for example, you can start asking people about religion, but maybe you don't really want to know who is of what, of what religion. You just want to know the statistics. So like, are we more Christians, or what religions do we have in the room, or what sexual orientations and things like that. You don't want to say who's what publicly, but you just want to know like roughly how many people of which category do we have here. So that would also be an example where we somehow want to say that, yes, there is one of us that is like that, but we don't want to reveal who that is. So the parties in the protocol are going to be one Alice, and this will be our sender, but somehow we call the sender Alice because we want to know who the sender is when we describe the protocol, but in the end we will see that from the outcomes of the protocol we will not be able to say who Alice was. And then we will have other parties, and we'll call them Bob1 to Bob n-1, because otherwise I would have to go Bob Alice, Bob Charlie, Danny, and whatever, and just number them. The initial state. Okay, who guesses the initial state correctly will get the chocolate from me.
0 to the n plus 1 to the n.
Okay. So chocolate or cookie or... No, really, if I promise something, I hold up to it, so...
I don't mind.
Okay. And moreover, so the message is going to be that Alice has a bit, which is either 0 or 1. We don't know whether it's 0 or 1, because that's the message she's trying to say to all of us. But Alice knows what this is, and she wants to broadcast this to all of us such that she does not reveal her identity. Actually, could we do that classically? So in principle, you can also do this classically, but then you need something like a shared keys between pairs of people, and they somehow manipulate these keys in order to come up with a similar protocol. Here we will not need shared keys, we'll just need the GHZ state. Okay. And here's the protocol. The first step is that Alice applies sigma z if b is equal to 1 and nothing otherwise. The second step is that each party, and now each means Alice plus Bob 1 to n minus 1, applies the Hadamard, which is a unitary defined such that h of 0 is plus and h of 1 is minus, where these states are the equal superpositions of 0 and 1 with varying signs. And then each party measures and announces the outcome. Announces. So each party will just measure and publicly say, this is what I got. And the 4 is that K is going to be the sum of outcomes. The sum of outcomes, or the sum of the outcomes where we had like a equals 1. Okay, so if you denote the outcomes by 0 and 1, it's exactly the sum of the outcomes. Otherwise, you would sum the outcomes where you had a equals to 1 and not the other ones. And the value of b is going to be k modulo 2, which means it's if k is even, this is 0. If k is odd, this is 1. So this is k mod 2, or whatever notation do you use usually in Germany?
The right one.
This one. Okay.
In maths at least.
Okay.
Programming the left one.
Yeah, this is like from Python. So I usually boil down to this one because it's shorter than that one. Okay. So we need some preliminaries. And this is that if we apply the Hadamard to the zeros, we get many of these things. And now in principle for each of these states we want to plug in this decomposition. So what we get is that we get 1 over 2 to the power of n, and here's going to be sum of x in 0, 1 to the power of n x. This is just the product of these coefficients, so nothing going on here. What this sum is, that it's running through all possible strings of zeros and ones of length n. So it's like 0, it's a set 0, 1 to the power of n. And then we are summing over all of them, okay? So for example, for n equals 3, that sum would be 0, 0, 0 plus 0, 0, 1 plus 0, 1, 0 plus 0, 1, 1 plus 1, 0, 0 plus 1, 0, 1 plus 1, 1, 0 plus 1, 1, 1. Just all possible strings of zeros and ones of length 3, or in general of length n. What happens in the other case is very similar. But now we are going to have some minuses here. When will the minus appear in the sum? Yeah. When we have odd number of ones. Because if there's product of even of them, then it's... Yeah. So we are going to denote this, the number of ones, and it's also called the Hamming weight of the string. So now the calculation. Or maybe let me just go to a fresh whiteboard. And here's the thing. After the step 1, we get state psi. What's going to happen in the state 1? Alice is either applying or not applying sigma z. Well, if she does nothing, we know we have this thing. And if she does something, then what's going to happen?
Sigma z was the bit flip.
The phase flip.
So that's minus.
So there's going to be plus minus here, depending on the value of b. For b equals 0, it's going to be plus. For b equals 1, it's going to be minus. So it's going to be plus minus 1 to the power of b. The thing is that already at this point you can see why we cannot identify Alice. because the same thing would happen no matter who would apply the sigma z. So already at this point, Alice did her thing, and from now on we cannot really reconstruct who was Alice. Whoever would have done the face flip would have landed in the same state. Very well. After 2, we apply the Hadamard's. And now we can undo this as a linear combination. So we get with, and now if you see, there's always 1 to the power, square root of 2 to the power of n. So and there's one more of them here. So it's going to be 2 to the power of n plus 1. And first is that we get this one from the first, this one from the second. So there's going to be sum over x, and there's going to be x from the first thing, and there's going to be minus 1 to the power of b, minus 1 to the Hamming weight, and then x again. Now by the trivial operation of spotting that this is the same vector in the sum, we can just pull it out. We get this one. Now this is going to be either 0 or 2, because we either get 1 plus 1 or we get 1 minus 1. When is it going to be 0 and when is it going to be 2? So if we don't know in general, let's do it case by case basis. And then we can have a neat formula in the end. So if this is going to be 0, then the b disappears, and we have 1 plus minus 1 to the Hamming weight of x. And so it's going to be plus 2 only if the Hamming weight is even, which means x has even number of 1s in it. And if b is going to be 1,
It's 2, it's okay.
yeah. So now what happens when all of the parties, where all of the parties measures the outcomes, they just collapse this superposition to pick one concrete string x, but we know, so in principle they all know the string, or once they somehow make their measurement outcomes public, we can reconstruct the string, we can compute the number of ones, and if it's even, we know that b was 0, if it's odd, we know that b was 1. Which is exactly that formula. And this is how we can do it. This is how we can use quantum theories to protect whistleblowers or collect some statistics. Are there any questions about this? There's one more thing, is that we should discuss the case where when more than one party wants to send a message, because if we are protecting a whistleblower, there can be more than one whistleblowers, and when we are collecting statistics, there can be more than one people that belong to this same category or something. But then we can do what's called collision detection, so we can somehow take more GHZ states and take more states and somehow agree to roughly when nobody's going to broadcast or when only one person is trying to broadcast the message and things like that. So in principle, also those cases are figured out.